We're going into the second chapter of the textbook now during this topic, and the topic of the second chapter of the textbook is all about stress transformations. So in this video, we're going to talk about how you can transform a state of stress from 2D in 2 dimensions. All right. So what is this? The first thing we're going to do here is what is a stress transformation? So a stress transformation is when you take a known state of stress, let's say that's in the x, y, and z coordinate system, and you're going to convert it to another coordinate system, all right, which is, let's say, the x prime, y prime, and z prime coordinate system. Okay, all right. The reason this is important in engineering and we need to know is that we want to determine the magnitude and the orientation of our maximum stresses. Okay, so these maximum stresses are often referred to as we want to find the uh, our goal is often to find the principal stresses. All right, these are our maximum stresses that are all right. Right? And we want to know what are the principal stresses, so what are the magnitudes of the principal stresses for a given state of stress, and what is the orientation or how are those principal stresses oriented. Okay, so we're going to get into principal stresses and orientations later on, but for now we're just really interested in converting a state of stress from our x, y, z coordinate system to our new coordinate system, x prime, y prime, and z prime. Okay. So in this video, we're going to focus on just a 2D transformation. Okay, so we're going to be going from XY, our XY system here, to our um, an X prime, Y prime coordinate system. Okay. All right. So in this case, we're going to be focusing on a case of plane stress. So we're going to ignore sigma z, tau yz, and tau xz. They're all going to be equal to 0. Okay, so we're only worried about the only stresses that we're worried about on our stress element are sigma x, sigma y, and our shear stress tau xy. Okay, all right, and then so what we're going to do is to go from the x, y coordinate system to the x prime, y prime coordinate system. All right, is we're going to rotate the system by an angle theta. All right, so theta, we'll consider that theta will be positive when the rotation is counterclockwise. All right, so in order to do this rotation, we're going to look at this element here. All right, we're going to cut it in half along the diagonal. All right, so so that's what this picture on the right hand side is. We have our element that's cut in half. Okay, all right. All right, and along this internal surface that we've cut, all right, is our new stress, sigma x prime. It goes along the x prime axis, and our shear stress, tau x prime y prime. Okay, so the other stresses that we had originally applied in our original element are still there. We have sigma y, we have sigma x, and we have tau xy also being applied. Okay, so what we're going to do is using this new element, we're going to sum all of our forces in the x direction and set them equal to 0. So we're going to start off with our sigma x prime here. All right, so sigma x, so remember that stress is equal to force divided by area. Therefore, force would be equal to stress over area, and you can say the same thing um, for shear stress. You can say that force would be equal to the shear stress times the area. Okay? So using those relationships, we're going to be able to solve for the forces due to all the stresses acting on this element along the x-axis. So for sigma x prime, the component of sigma x prime that's going along the positive x-axis would be equal to sigma x prime times cosine of theta. All right, and then multiply that by the area that the stress is applied over. So the area is going to be the area that's like the hypotenuse of the triangle, which we'll note as delta A here. All right. In a similar fashion, we can look at the shear stress that's acting on the system here. And the shear stress is going to be equal to the force due to the shear stress is going to be equal to um, minus tau x prime y prime times sine of theta times delta A. All right, so this is our force times our area. All right, sorry, our stress times our area, okay, along the x-axis. All right, and then we have two additional terms. We have sigma x, which is going along the negative x-axis, so we're going to include a negative sign, and it's going to be multiplied by delta A cosine of theta. Right? And then our last is our shear stress going along the x-axis is going to be equal to minus tau xy times the area that is multiplied off of, which is delta A sine of theta. All right? If we rearrange this equation, we can put the prime terms on one side of the equation and the unprimed terms on the other side of the equation. And we can divide both sides by delta A, and we end up with equation number 1. Okay? In a similar fashion, we can do the same thing for the sum of the forces along the y direction. Right? So for the y direction, we'll include all of our stresses. So for sigma x prime, we would get sigma x prime times the sine of theta times delta A, and we would add tau xy times the cosine, tau x prime y prime times the cosine of theta. Again, it's going along the positive y-axis, so it's going to be a positive sign times delta A. And then we'll include the remaining terms from our unprimed stresses. So we have minus sigma y times delta A sine of theta. And then we'd have shear stress that's going along the y-axis, which is going along the negative axis as well. So we have tau xy times delta A cosine of theta. All right. So if you move all the unprimed terms to the other side of the equation, we can divide by delta A, and we end up with equation number 2. Okay. All right. So if we then cut our original element again, but instead of cutting it along the y prime direction, we cut it along the x prime direction. All right. All right. All right. We would leave this internal surface. All right. And we could repeat the process where we sum all of our forces in the x direction and sum all of our forces in the y direction. And after we do some simplification, we'd end up with these two remaining equations. Right. All right. So we can rewrite equations 1 through 4 into matrix form. So if we do that, what we end up getting is we would get sigma x prime times tau x prime y prime sigma y prime and tau x prime y prime times cosine theta times sine of theta and then we'd have minus sine of theta, and we'd have cosine of theta. All right, and we'd have cosine theta, sine theta on this side. We'd have minus sine theta and cosine theta on the bottom, and then we'd have our original stress matrix on the right. All right, so we can write this in shorthanded form as sigma prime matrix times the transformation matrix, which is this matrix full of sines and cosines, times the is going to be equal to the transformation matrix times our original state of stress, sigma. We can multiply both sides of this equation by the transpose of t, right? All right. All right, so if we do that, this is what our equation will now look like. All right. The good news for us here is that t, if you multiply t times the t transpose, what you end up getting is you end up getting the identity matrix. So the identity matrix in this case would just be equal to 1, 0, 0, 1. All right. And so if you any matrix times the identity matrix, you just get the same matrix. So what we end up getting is we get sigma prime is going to be equal to the transformation matrix times our original stress matrix times the transformation matrix transposed. All right. So that is our general equation that you can use to transform it from one state of stress to the other state of any other state of stress. The only thing that you need to know is the original state of stress and what is your transformation matrix. So if you're given the transformation matrix and you're given a state of stress, you should be able to relate any state of stress to a new state of stress. Okay? So that equation I wrote on the last page is the same equation here. Sigma prime is equal to the transformation matrix times the original state of stress times the transformation matrix transposed. Okay, so just to reiterate, what we just did is using this equation, we went from our original state of stress, which is defined here, to our new state of stress, sigma prime. Okay, all right. So you can also, if you don't want to use matrices, you can use these. If you multiply all those out, you can get that matrix out. You can get these three algebraic equations here for sigma prime, sigma y, and tau x prime, y prime. You could also write those three algebraic equations using in matrix form as well, with a 3x3 transformation matrix and a a column vector instead of row vectors. But that is the so in conclusion, what I just wanted to iterate here is that if you know the angle theta between the two coordinate systems that you're transforming against, and you know the original state of stress, you should be able to solve for the new state of stress, so your new normal stresses and your new shear stresses in 2 dimensions.